Alright, so now we want to make sure we really understand related rates. Like, how are you related to your rates? It's a good question, right? So there's just going to be a lot of work on your part. But like the great Mike Jones said, you don't work, you don't eat. You don't grind, you don't shine. Alright. So, a plane is flying away from an airport at an altitude of 5 miles. When the plane is 10 miles away from the airport, the distance from the airport to the plane is changing at a rate of 240 miles per hour. What is the speed of the plane? So try this on your own. Hint, right triangle. Pause the video and pause when you're ready to check. Alright, so assuming I've done my math correctly, which I make mistakes, the speed of the plane is 160 root 3 miles per hour. One thing you always want to think about also, does that actually make sense? Like, is that a reasonable speed? Yeah, I mean, depends how long the plane's been flying for, but yeah, it's like 270 something probably. I think, yeah, 277 on my calculator. So, yeah, that's reasonable. Not super fast for a plane, but reasonable. So, okay, let's look at our picture. How do we come up with this? So here's the airport, there's the airplane, check out that plane. That's a nice plane. I'm calling the hypotenuse of this triangle x. I'm assuming the plane is flying at a level, horizontal to the ground, straight path. And it is 5 miles in the air. So this 5 is a constant, okay? This is z, this is x. So I know x is 10 at the instance that I care about. dx dt is 240. dz dt I don't know. That's what I'm trying to find. I also don't know z at this point. This is not a special right triangle, so I need to do a little Pythagorean theorem off to the side to find what is the actual distance of z right now at the instance that we care about. So 5 squared plus z squared is 10 squared, so z is 5 root 3 miles. Alright, again, this was just so that I can find when x is 10, what is z. Alright, but z is still a variable. So now I go back to my Pythagorean theorem with the z and the x as variables. 5 is a constant, do the derivative, 0 plus 2z dz dt equals 2x dx dt. Z is 5 root 3, x is 10, dx dt is 240. Solve for dz dt, I divided by 5 root 3. I rationalized in this case. Again, I've said you don't need to rationalize, and that's fine if you leave it as 480 over root 3, but it rationalizes pretty nicely to 160 root 3. And then we write the answer in the context of the problem. So again, the new thing on this one that we haven't done yet was having to use our equation, which in this case is Pythagorean theorem, before the derivative to find one of the other values that we're going to plug in after the derivative. Okay? So that's something that sometimes we might have to do. Next one. Let A be the area of a circle of radius r that is changing with respect to time. If dr dt is constant, is dA dt constant? Explain. So I want you to think about that. Alright, this isn't a solving, this is just kind of think about how they relate. I will give you a hint. Use the area equation of a circle to understand your answer, or to come up with your answer. Pause the video, unpause when we're ready to discuss your explanation. Alright, so here I said no. Did anyone say anything different? No? Or, hold it, no, you didn't say something different, or no is what you... No. Alright, so I said no because even if dr dt is constant, dA dt is still dependent on r. So if r changes, so will dA dt. And how I'm coming up with that is, okay, my area equation, area equals pi r squared. So dA dt is 2 pi r dr dt. So even if this is a constant value, if this changes, so will this. So a way to think about, okay, well, what would an example be where this would have been true? And that would be if I have some equation like this, and when I do the derivative, all the other variables go away. So if this ended up with just dA dt equals 2 pi dr dt, then dA dt would be a constant if dr dt is a constant. They would be directly related to each other. In this case, it's not, because I still have another variable here. Next one. A spherical snowball melts in such a way that the instant at which its radius is 20 centimeters, its radius is decreasing at 3 centimeters per minute. At what rate is the volume of the ball of the snow changing? So you're trying to find dV dt. You need to know the volume of a sphere. So again, you could use Google, your book, any of your other resources, your memory, or you can just understand that volume is 4/3 pi r cubed. Pause the video, find this, unpause when you're ready to check. Hopefully this one was pretty straightforward because we didn't have to do really any substitutions for variables. So volume of the snowball is decreasing at 4,800 pi centimeters cubed per minute. Again, context, crucially important here. So we know volume is 4/3 pi r cubed. I know that the radius is 20 centimeters at the instant that I care about. I know that dr dt is 3 centimeters per inch. I'm sorry, 3 centimeters per minute. So then I find the derivative. dV dt is 4 pi r squared dr dt. Plug in r, plug in dr dt, simplify, and I get 4,800 pi centimeters cubed per minute. So I know that the volume of the snowball is decreasing because I knew that the radius was decreasing. So although I left this as a positive value, the context is going to carry through. If I wasn't sure, I would have put this as negative 3 centimeters per minute to see that I would get a negative dV dt, so therefore I would know that it's decreasing as well. Next one. A thin uniform rod of length y centimeters and a small particle lie on a line separated by a distance of x centimeters. If k is a positive constant, so we know that this is a constant and it's positive, and F is measured in newtons, the gravitational force between them is below. So if x is increasing at 2 centimeters per minute when x is 15 and y is 5, how fast is F decreasing? So I want you to pause the video, try this one, unpause when you're ready to check. Alright, so here F is decreasing at 7k over 9,000 newtons per minute. Alright, how do I come up with that? So one thing I want to emphasize is it's really important to recognize, okay, k is a positive constant. So we're going to have k in the answer, potentially. In this case, we know we do because we just saw the answer. But it is a constant, so that's going to help us. So we know that y is 5, but y is also constant because that's the length of the rod, and we're not talking about the rod changing in any way. So dy dt is 0. We know x is 15 at the instance that we care about, and we know dx dt is 2 centimeters per minute. dk dt is 0 because it's constant. df dt is what we're trying to find. So first I rewrote the equation so that, again, I'm not going to do the quotient rule where a constant is the numerator. So F equals K, quantity x squared plus xy to the negative first, bring down the negative 1, make that to the negative 2, times the derivative of the inside. I have to do the product rule here, but dy dt is going to be 0. So actually, I'm sorry. This is an example of where I didn't need to do this. I could have just plugged in the 5 right away for the y. Because I know y is a constant, I chose to do the product rule and treat it as a variable. That was a choice I had, but you could have plugged in the 5 right away. That would make this a little bit simpler, actually. So df dt then, now I'm just going to simplify. I brought this down to the denominator. Look at this, plug in the values, and I end up with negative 70k over 90,000. So I can simplify to negative 7k over 9,000. So then I just answer in the context of the problem that F is decreasing at 7k over 9,000 newtons per minute. Again, I just want to go back up here and emphasize. So this is an example of where I could have plugged in the 5 for y before I did the derivative because I identified y as a constant. Next one, and conveniently the last one. A train is traveling at 0.8 kilometers per minute along a straight track going east. The camera 5 kilometers south of the track is focused on the train. How fast is the distance from the camera to the train changing when the train is 1 kilometer from the camera? Try this one on your own. Hint, it's going to be a right triangle again. It's important to also recognize when we say it's going east, that means it's going straight east. So that's going to help you with drawing your picture. And also when we say south, that means straight south. Pause the video, unpause when you're ready to check. Okay, so the distance between the camera and the train is increasing at 2 root 3 over 5 kilometers per minute. How do I come up with that? Okay, so this is my picture. Here's the camera. That's fixed. The train went by the camera and is still moving east. So the train's somewhere over here now. This is my y, this is my x, this is my z. I know that y is 0.5 kilometers and that y is a constant. So dy dt is 0 because the camera's not moving. These are the tracks. Those are not moving either. It's just the train that's moving along the tracks. dz dt is what I want to find because that's how fast the train is moving away from the camera, but dx dt is how fast the train is going, so I know that. That is 0.8 kilometers per minute. And I know the instance that I care about is when z is 1. So first, this is similar to the airplane problem we did. I need to actually find what is x in terms of the other lengths. So y is 0.5, z is 1, so I can find x. X is root 3 over 2, and maybe I could have figured that out also by recognizing, okay, if one of the sides of a right triangle is half of the hypotenuse, that means this is a 30, 60, 90 triangle, so the other side is going to be 1/2 root 3 or root 3 over 2. If I didn't recognize that, that's okay. Alright, so I'm using the Pythagorean theorem then for my derivative. Again, I could plug in my constant for y. In this case, I just chose not to and just do the derivative, and then I made that 0 afterwards. But it doesn't matter. So I did the derivative, plug in the values that I know, solve for dz dt, I get 2 root 3 over 5. So the distance between the camera and the train is increasing at 2 root 3 over 5 kilometers per minute. Okay, related rates. It's important that you read carefully. Identify what's a constant, what's a variable. Follow the guidelines. Guidelines are important in life. Math's life, follow the guidelines. Take your time, do it right, you got this.